All right, so the two things I want to just make sure everybody understands are that, first of all, on Wednesday, when you come in, we're going to very quickly have some time to document what you've done with rotation and get it turned in. So that's going to be mostly just like taking pictures of stuff and turning it into me. And then most of the day on Wednesday is going to be devoted toward essentially going through the same exercise that we've been going through. We've been looking at rotation. On Wednesday, we're going to look at energy and work. So I had you all like a month ago take some measurements and make some tests involving springs and carts. I said, well, get the spring pushed in on a cart and figure out how much energy is stored in there by using what you know about springs, then launch it and predict how far up a track it's going to go. A whole bunch of you did that. Some of you really got it completed. You've got all your thoughts documented. Many of you didn't. Some of you didn't get anything done. Some of you got only part of it done. And a lot of that was because AP tests were coming up and people were gone for robotics. And so we're going to revisit that, but we're going to revisit it relatively quickly. I'm going to have you think about something different. It's not going to be the exact same challenge. I'm going to have you kind of come up with your own idea of things to think about. But what I would like is for you to be able to demonstrate your understanding of energy and work, to think about our energy buckets of kinetic energy, gravitational potential energy and elastic potential energy, to think about how work transfers energy between those buckets, to think about the fact that work is always force being exerted on an object that's moving in the direction of that force. And I'm going to be looking for you to show me the same kind of conversational skills that I'm looking for with rotation. I don't expect everybody to be able to get every question right, to know everything, to have all the equations memorized, to be able to make every single prediction to, 30 decimal places of accuracy. What I want is to be able to talk to you about work and energy and have it be the kind of thing where it's very clear that you were focused, you were paying attention, you were engaged in what was going on. And as long as I see that, then the work that you turn in that is kind of demonstrating your ability to do this stuff is going to be meaningful to me, okay? So that'll be Wednesday. And then on Friday, we're moving on. We're going to start talking about oscillations and other sorts of things. So just be aware that those of you who have been here, who have been focused, who have been engaged, who really understand what's going on, the work you do today and Wednesday is largely going to be an exercise in just kind of convincing me that that's the case. If you were gone, if you missed a bunch of class for robotics, if you were thinking about AP tests, if you were gone for AP tests, if you weren't engaged for any one of a number of reasons, then don't panic, but, thank you, but you will need to maybe do some work outside of class, because you might not know this stuff if you weren't here, if you didn't learn it, if you were focusing on AP classes or something. So then you might have to do some stuff outside of class. And it might be that when Wednesday rolls around, you don't have much to show for your understanding, and that's okay. It just means that we'll kind of set that aside, and then you'll have to come back later outside of class and demonstrate that understanding. So you may have to go figure some stuff out on your own, watch some of the videos that I've posted, watch other videos, read the book, talk to other people, talk to me, and then at some point we'll sit down and I'll say, okay, tell me an energy story that makes sense, and at that point you'll be able to do it, and maybe that's not Wednesday, maybe that's 2 weeks from Wednesday. But it's going to be on you to make sure that that happens. And I just want to be really clear that my baseline is you were in class, really focused and engaged, trying to figure stuff out. If you've done those things, you're good. If you haven't done those things, it has to happen at some point, either between now and Wednesday or after Wednesday, at which point you'll need to demonstrate it to me at a later time. Yeah. Okay. All right, so that's Wednesday. for today, what I want to focus on is I want you to potentially start setting things up for your rotation challenge, but many of you may not get there. And I tried to emphasize this on Friday just to make sure that it's very clear. If we had time, we could do all these things. There's no doubt in my mind that you all have the skills that it would take to get these things done. But in the amount of time that we have, some of you are going to be like just still drawing and writing. You're not going to have the ability to work with actual materials and actual tools and actual equipment to do anything, because you're going to be figuring stuff out, and that's okay. I'm not asking you to actually do this work, but effectively what I'm looking for is I want to see drawings, diagrams, oops, that's a homework diagram, drawings, diagrams, a list of proposed measurements and calculations. Some of this work you've done already, you did it on Friday, but this is the documentation that I'm looking for. And effectively, what we're doing is three things, okay? And where the conversations come is your ability to kind of follow the reasoning here. If what I'm about to say is absolutely crystal clear to you, makes perfect sense, you get what I'm asking, then you're going to be in great shape. We're going to have some really good conversations and may uncover some things that you need a little bit of work on, or maybe not. Maybe you really got everything nailed. That'd be great. If what I'm saying right now, what I'm about to show you, you hear me and you're like, I don't get it. I don't get what we're doing. I don't get how to find any of these things. Then that's okay too. It just means you've got some work to do. This is the stuff that I want you to figure out. Okay, and this is what we did in class with the concentric pulleys and with the vernier systems, all right? It started by finding moment of inertia. For your system. So this is a piece where, there's a conceptual part to this. If you don't understand what moment of inertia is, if you don't get that moment of inertia is a property of a system relative to a certain axis of rotation, then it's probably not going to make sense to you to be like, find moment of inertia, because like, how do you do that? What's the point of finding moment of inertia? Finding moment of inertia of a rotating object is like finding the mass of a non-rotating object. Once you know it, you can use it to make a bunch of other predictions. If you tell me, hey, I'm going to go outside and I'm going to push on that box with a certain force, how far is it going to go if I push for like 6 seconds? I can't answer that unless I know the mass. If you tell me it has the same mass as this sponge, then it's going to go pretty far. If you tell me that it has the same mass as that filing cabinet, it's not going to go as far. Rotation depends on moment of inertia. So if you can find moment of inertia, then you can make all sorts of predictions. We talked about how to find moment of inertia for the concentric pulleys because of the way these things work and the fact that they have a very low moment of inertia. It made sense to hang two masses. One mass off one pulley providing torque in one direction, one mass of another pulley providing torque in the opposite direction, just so that you could get a reasonable amount of tension in the strings without having like the concentric pulley just go bzzz and not be able to make any measurements. So, but with the systems that you're setting up, you might not need to do that. Like many of these objects that you're actually talking about rotating have a large enough moment of inertia that you can easily find it by just hanging one mass. It's not going to accelerate super quickly. So you're going to get some masses. You're going to get some pulleys. You're going to make some measurements, and you're going to use those to calculate moment of inertia, and I'll show you in just a second what I mean by that, okay? Once you've done that, then you are gonna make a change. And this is where a lot of you are like, wait, what? Like, didn't I already do this? Don't I already know this? Finding mass of a linearly moving object allows you to make predictions under different circumstances. If you tell me an object's mass, and then you say, well, I'm gonna push on it with 5 newtons, I can make predictions. If you say, actually, I'm gonna push on it with 12 newtons, I can make predictions. If you tell me I'm gonna push on it with 30 newtons and somebody else is gonna push on it with 6 newtons, I can make predictions. As soon as I know its mass, I don't have to measure its acceleration to predict its acceleration. That's what we're doing here. We're finding moment of inertia, rotational mass, and then you're gonna change the torques you apply. So instead of just saying, okay, well, now I know moment of inertia, and I figured out its acceleration under a specific circumstance, now I'm done. What we're gonna say is, okay, what if we changed it? So you're gonna change the masses and locations of where the torque is applied, and you're going to calculate a predicted alpha angular acceleration. If you know an object's mass, and then you think about the kinds of forces that will be applied to it, you can predict what its acceleration will be. Once you know what an object's acceleration is going to be, then you can use that to predict things like how far will it go, how long will it take, how fast will it be going. With angular acceleration, we can predict things like how many rotations will it make in a certain amount of time, or how long will it take to move a certain angular distance or to achieve a certain angular velocity. These are engineering problems. Okay, so what I want you to imagine is like a motor that is being used to drive, say, an inkjet printer, like the print head in an inkjet printer, which moves back and forth. It's driven by motors and gears and stuff. If you're designing a printer, you need to know how long it's going to take for that print head to be moving at a certain velocity, because it's all based on timing, right? Like you tell it to spray some ink, not based on knowing exactly where that print head is, but in knowing how long it takes to get somewhere. Because you're spraying the ink, like, and the ink is moving as it sprays. So the ink is like, has a velocity. You have to know all the kinematics involved with the motor that is moving the print head in an inkjet printer back and forth. To do that, you need to know what its angular acceleration is going to be with a certain set of forces and torques on it. To do that, you need to know the moment of inertia of the motor. And that's the kind of work that we're doing. So this is what I'm looking for you to demonstrate to me, that you can find the moment of inertia of a system, just like we found the moment of inertia of our concentric pulleys. Once you've done that, you're going to think about, okay, now if I apply a different amount of torque somehow, and what I specifically told you is that that torque should be applied in 2 different directions, right? So you're going to have one torque that is tending to cause counterclockwise rotation, and one torque that is tending to cause clockwise rotation. So it's got to be, that's part of the parameters of the problem, is there's got to be 2 torques on it, one in one direction, one in the other direction. But given these 2 torques, how much angular acceleration will you get as a result? And then using that, you can predict things like how far will it go. When we found moment of inertia for our concentric pulleys, we used this equation, and I developed this equation for you. I don't expect you to be able to do the algebra here. When you all find the moment of inertia for whatever it is that you've been thinking about, you might be applying 2 torques in 2 different directions from 2 different masses, in which case you could use this same equation. Or it might be that you're only applying torque in one direction or the other direction, which means you can still use this equation, it's just that one of your masses is going to be 0. you go back to what we did, mass 1 providing positive counterclockwise torque, mass 2 providing negative clockwise torque, maybe you just hang something off of one side that would tend to cause counterclockwise torque. This mass is 0, and you can find moment of inertia just by knowing the only mass and its distance from the center of rotation. Measure the resulting angular acceleration. You can use that to find moment of inertia, okay? So this is how you're going to find moment of inertia. And once you've done that, then you're going to use that to predict a new alpha under new circumstances. And I know that some of you can do the algebra, which is great. Some of you won't be able to, and that's fine too. I don't really care about the algebra. I want you to just understand that this equation has the same number of variables in it, no matter which one you're trying to find. In this case, we're saying we're going to measure our masses. We're going to measure the distances that those masses are located, that the forces are being applied to the center of rotation. We're going to make some measurements and calculate the resulting angular acceleration. And with that, we can find moment of inertia. Now what we're saying is use the same set of variables, but instead of finding moment of inertia, you're now going to find alpha. You already know moment of inertia. So algebraically, if we multiply both sides by alpha, we get something that looks like this. And algebraically, we can solve for alpha, get all the terms with alpha on one side, factor out alpha, divide by the rest, and you'll get an equation that says alpha equals like a bunch of stuff. The bunch of stuff is going to have moment of inertia in it because we know it now. We figured it out. It's a property of the system. It's not going to change unless we change the mass or the axis of rotation of what we're using. So I'm not going to do this part for you because it's not important to actually do the algebra. I just want you to see that that's what we're doing. We are using a different mass, different distances, but we now know the moment of inertia. So once we know moment of inertia, we can use different masses, we can apply the forces at different distances to the center of rotation, and we can predict the resulting angular acceleration, right? So this is your job for today, and I'm gonna turn the video off so that we can ask questions without you all being on film.